thank organizers for inviting me and giving me the possibility to attend to this very interesting symposium. I have to apologize that we don't really do much of spectroscopy in our lab, but we really like to work with the compounds which have rare earths and transition metal ions. And I hope I will give you some interesting overview of how these materials are extremely important for the field of ultrafast magnetization dynamics. Start from the very brief historical overview, which of course will not go as far as overview given by Professor Pisarev. Just to the end of the last century, when in 1996, there was a very first successful experiment showing that ultrafast laser-driven magnetization dynamics is actually possible. The experiment was performed on nickel, which is ferromagnetic metal. It was shown if you take a femtosecond, 100 femtosecond laser pulse, excite this material, then magnetization suddenly drops by really large degree, by 50% or so. And this drop happens on a time scale which is shorter than 1 picosecond. Then it is followed by some slower relaxation. And this experiment was the first demonstration of so-called ultrafast demagnetization. This effect is still a matter of really hot debates and discussions. There are more and more sophisticated and advanced experiments are performed to really understand this process. But so far, it is general understanding that this all ultrafast laser-driven magnetization dynamics relies on the fact that our laser pulse is so short, and the processes which laser pulse excites in the material happens on such a fast time scale that this time scale appears to be faster or shorter than some characteristic time scales within the material, like electron-phonon coupling or spin-phonon coupling, and so on and so forth. And since we really bring the material to some really non-equilibrium state, very interesting processes start to happen which are not possible with longer pulses. Since 1996, there was a lot of demonstrations of different effects, like ultrafast changes of magnetic anisotropy. Now there are ongoing attempts to demonstrate ultrafast changes of exchange interaction. Also, there are some inverse magnet-optical effects. Well, for example, for some review, you can refer to our recent big review in physics reports. And today, I would like to convey the main message of my talk, which is basically in materials that, from the point of view of materials which have different subsystems, for example, different magnetic ions, and these magnetic ions couple differently to lattice or to light. So, from this point of view, magnetic materials which have rare earth and transition metal ions magnetically ordered is extremely important and extremely interesting materials. And actually, this kind of combination allows us to realize, for example, switching of magnetization by light. First, there is I very briefly will introduce probably the most famous experiments in this field, but I will not go into details because it's about metals, so it's really far from the subject of the symposium. But in principle, maybe the most striking demonstration how rare earth transition metal compounds can help us to switch magnetization is so-called all-optical magnetization recording or magnetization switching, which was found in rare earth transition metal compounds like gadolinium, iron, cobalt. This is metallic ferrimagnets. The magnetic structure is shown here. And this is one of the main experiments. Basically, what is shown here is magnetic-optical images which show the orientation of magnetization, which were taken with a very high temporal resolution after excitation of this material with 40 femtosecond laser pulse. So first we have a white area which shows that magnetization was, for example, pointing up. And then after several picoseconds, we see some gray area. And then already after 50 or even 30 picoseconds, we see black domain, which shows that magnetization switched. And it happened without any external magnetic field. So for a while, it was really a mystery what's going on. But then a very important experiment was performed. It's actually now, it's a little bit about time-resolved spectroscopy. Basically, it was time-resolved XMCD measured for iron and for gadolinium. And it was shown that actually when we excite the material with such kind of material, with short femtosecond laser pulses, there is demagnetization in iron and gadolinium, but they happen on different time scales. And apparently, this is one of the key elements of this kind of very exotic and very important switching. was also reproduced in some theory, but the main point here is that this switching wouldn't be possible if we would have only iron or only gadolinium. It is presence of two magnetic ions which respond differently to laser pulse heating, ultrafast laser-induced heating, which really drives the switching. But today I would like to focus on two different materials. That will be rare earth orthoferrites, where we have shown laser-driven spin orientation transitions. These are published results. And also laser-driven switching via compensation point in rare earth iron garnets. These are the very new results. So, yeah, these are the co-authors on this part of the paper. And first, rare earth orthoferrites. It's quite well known in magnetism materials. These are dielectrics. Magnetization here comes from the ordering of iron magnetic moments. In principle, they form 4 antiferromagnetically coupled sublattices. There is also small canting of the sublattices, so it's weak ferromagnet. We can describe it using ferromagnetic and antiferromagnetic vectors, F and G. And what is important that apparently in this material, anisotropy is very sensitive to the temperature. Below the Néel temperature in these materials is above 600 K. Below Néel temperature, we have weak ferromagnetic moment pointing along this axis. It's the C axis of the crystal. However, at certain temperature, which is dependent on the type of the rare earth ion which we have here, spin orientation transition happens. And actually, the magnetic moments rotate, and we go to this gamma 2-4 phase with magnetization pointing between C and A crystallographic axis. If we cool down the material further, there is second spin orientation transition happens, and now we have gamma 2 phase with magnetization pointing along the A axis. In principle, this kind of transition is not possible to describe in terms of just single ion anisotropy, and it was very intensively investigated in 70s and 80s of last century, and it was suggested that in principle there is a competition between two contributions to magnetic anisotropy. One comes from the single ion anisotropy of iron ions, and this is the anisotropy which stabilizes this gamma 4 phase. But at low temperatures, another contribution starts to play a role and starts to dominate, and this is basically a single ion anisotropy of rare earth ions and their coupling to the iron sublattice. Because at low temperature, magnetic moments of rare earth ions are large, therefore this magnetic contribution dominates. And actually, this also explains the fact that these temperatures are really strongly dependent on the rare earth type itself. So, in principle, if we heat up this material, we can really switch magnetization from one phase to another phase. Is it possible to do it by a femtosecond laser pulse? Yes, of course. If there is absorption, there will be heating. And in principle, we should be able to go from one phase to another one. It was first demonstrated in 2004 by our colleagues from Nijmegen and also by Roman Pisarev. So, is there anything special about this laser-driven transition? It is believed that it's based on laser-induced heating. But when it was investigated in details, so here it's shown the dynamics of Faraday rotation, basically dynamics of the ferromagnetic vector, one of its components, as a function of the time delay between excitation moment, after the excitation moment. It was found that depending on the temperature, how far we are below the spin rotation transition, this laser-induced transition will happen at different time delays of order of several or even 15 picoseconds. And it was suggested that, in fact, the mechanism behind this transition is the following. Usually we use femtosecond laser pulses, which we use to excite the material, which are in near infrared or visible range. Therefore, they are mostly absorbed by iron electrons. Then there is very fast relaxation and energy transfer to phonons. Basically, the lattice is heated up. And then, because of the electron-phonon coupling, which is rather slow on the time scale of several tens of 10 picoseconds or so, between phonons and 4f electrons of rare earths. In this case, it was erbium. This is basically when the transition happens. Basically, because of this coupling, the different crystal field split levels of rare earths are repopulated, magnetic moment changes, and as a result, a spin orientation transition occurs. So there is some kind of a delay or bottleneck. So is it good or bad? Actually, we can try to use it. Well, in principle, laser-induced spin orientation transition seems to be a nice way to really switch magnetization. So we start from the low temperature phase, we excite material, and we switch it to another phase. But the problem is that if we don't have external magnetic field, and typically we don't want to have external magnetic field, then in principle switching will happen from this minima to this, to either to this or to this minima of our potential energy. So this is potential energy profile at the low temperature, at high temperature. So basically, in experiment, it means that if we take our material, we excite it with a femtosecond laser pulse, we don't have any external magnetic field, we will end up in some kind of a multi-domain state. Can we avoid it? And basically what we tried in our experiments to do is actually we tried to find a way to use this delay, this bottleneck, in order to use the other properties of laser pulses to really control the way the magnetization switches during this phase transition. So this is our material. It was grown by Anatoly Balbashov. This is samarium praseodymium. The choice of the material was mostly motivated by the fact that we wanted to have large magneto-optical response, and this is a really very good material for that. So spin rotation transitions happens at, let's say, just above 90K and at something like 130K. This is our experiment. Basically, yesterday, Dr. Yusuf Foldi introduced the idea of the pump probe experiments. Here it was somehow a little bit more complicated one. So basically what we used femtosecond laser pulses, single femtosecond laser pulse. We excited the material, which was in low temperature phase. And then we used the delayed, very short probe pulse to get the magneto-optical image of our sample, basically to observe what is the orientation of magnetization at a particular time after the excitation. And we can take these images at different time delays. This is the result. First, we use the linear polarized light. So this is a negative time delay. It means that this is image before the excitation. We have some gray area. It means that magnetization is in plane, and we don't see any magnetic contrast. But then after the excitation, or after several picoseconds, we see some kind of white or brighter and darker areas, which actually correspond to magnetization starting to reorient out of plane. And we get gamma 2-4 phase, with magnetization pointing a little bit up and a little bit down. It's actually what we expected, multi-domain state. But now, if we change the polarization of our pump pulse, if we make it circular polarized, then we see that only black domain emerges. So we have switching from this phase to this phase. And if we change the circular polarization, then we have switching to the another domain. So basically, we have ultra-fast laser-induced spin orientation transition induced by the single femtosecond laser pulse and controlled by the polarization of this pulse. So what's going on? Our idea is the following. So if we have linear polarized light, this is our low temperature phase. This is potential energy profile. So we're in the minimum. Then this process, then we have excitation, we have ultrafast heating, we have this process, and after several picoseconds, two potential minima emerge, and magnetization and our system can go to this minima or to this minima. If we change the polarization and use circular polarized light, then we know that circular polarized laser pulses can induce something which is called ultrafast inverse Faraday effect. Briefly, this is when we have circular polarized light, it acts on the material as a very short pulse of the effective magnetic field, and it can trigger the precession. So therefore, the precession will have low amplitude of few degrees maximum, but this means that right after the excitation, our system will start to oscillate here. So basically, it will deviate, for example, in this direction. And then when these two minima emerge, our system will prefer to go to this minima. If we change the polarization of the pump pulse, then initial phase of this excited process changes. We know it from experiments, and therefore we'll end up in different minima. So basically, we use this bottleneck, and we combine our heating with the ultrafast inverse Faraday effect, with excitation of low amplitude precession, in order to control spin orientation transition. And basically, we kind of lift the degeneracy between these two states dynamically. What is interesting that, in effect, this time, the time which required for this repopulation of the rare earth states and for emergence of this two minima, it was shown that this time is dependent on laser fluence and on initial sample temperature. And we can imagine that, if, for example, if this time will be longer than the half period of the precession, of the excited precession, the now system will go first here, then it will go here, and it can end up here. So it means that changing the fluence or initial temperature, we can also go to this state or to this state. And we did some modeling, and also we showed that indeed it is possible. It's kind of phase diagram. So here at low fluence and low initial temperatures, nothing happens. And at high fluences or high temperatures, we have transition to this or to this state. We can verify it experimentally. So this is the final state. After the excitation at low temperatures, we have black domain. And after excitation with at higher temperatures, we have white domain. Also, we had the very same pump polarization. So this brings me to the conclusions of this part, that in principle, the ultrafast spin orientation transition in rare earth orthopherites is enabled by ultrafast heating. And what is important, that there is this kind of a delay which is required to repopulate rare earth ions state. And we can use this delay, and we can combine this with the ultrafast inverse Faraday effect in order to control the way magnetization switches. So the second part is about rare earth orthopherites, rare earth garnets. It was done by our team at Ioffe Institute. Experiments were performed at BESI. This is an ongoing project. So iron garnets, like aluminum garnets in spectroscopy, are extremely important. Iron garnets, these are magnetically ordered materials which are extremely important for magnetism. This is working horse of magnetism. So in the iron garnet, there are two positions for iron. There are two magnetic sublattices. They are coupled antiferromagnetically, but there is imbalance between number of ions in these two positions. Therefore, these are usually ferrimagnets. So they have net magnetization. What is important, if we replace yttrium by some rare earth in these dodecahedral positions, this rare earth magnetic moments, they also order because of the coupling to the iron. In the end, we get this ferrimagnet where we have net magnetization of iron and net magnetization of holmium pointing in opposite directions. And what is most interesting, that there is a very different temperature dependence of magnetization of, for example, of holmium or other rare earths. It's shown by black dashed curve, and of magnetization of iron, which is shown by red curve. So there is a compensation temperature. Basically, it means that here, for example, if we apply magnetic field, the magnetization of holmium will be pointing along the field, and magnetization of iron will be opposite, and here it will be just reversed. So also, it was shown theoretically and also in some experiments by Zvezdin, by Professor Zvezdin, also by Harchenko and Yeremin in Kharkov. In the vicinity of compensation point, there is a very interesting phase diagram where some canted phases and so on are possible. So can we switch magnetization from here to here just by using femtosecond laser pulse? We wanted to really study it, but this time we wanted to study it by looking separately at rare earth and iron magnetizations. And for this, we of course needed something sensitive to different magnetic moments. And this is XMCD in the soft X-ray range. Basically, this is shown the spectra, reflected spectra for circular polarized soft X-ray at the energies of, for example, 715 or around 715 electron volts. This is a LH of iron, L2 free H of iron. We see that there is a difference in intensity depending on the orientation of the applied magnetic field. We can subtract them and get this kind of spectra. This is basically XMCD, shows orientation of iron into positions. If we tune the energy very far from here to 1,300 something electron volts, we can measure the same for holmium. So basically, we can really distinguish them just spectrally. It's very kind of simple. So now let's do the experiment. Let's use femtosecond laser pulse to excite our material. And let's use this X-ray pulses, but they will be very short. Therefore, they will have really low intensity. So it's very these experiments really takes a lot of time, but we'll do pump probe with this soft X-ray probe. And this is a typical experiment. Sorry, they are quite noisy, but still I think we can see important effects here. So black and red curves, these are just intensity versus time delay when we have no pumping. So there is some drift, but in general, basically contrast, which is the difference between these two curves, doesn't change. So no pumping, nothing changes. If we switch on the pump, we look at the green and magenta curves, and then we see that contrast between them starts to change, goes to 0, and switches. So we can just subtract them, plot it here, it will be magnetic contrast. We go from -1, we switch at something like 250 picosecond, and then really we see reversal contrast. So this is laser-driven switching via compensation point, most probably. And most importantly, that's quite slow process. Nothing really happens at the short time scales. Now, if we look at holmium, then we can do the same procedure. We also see this kind of slow dynamics, but most importantly, at short time scales, we see really fast drop of the signal. We can look at this closer. Well, it's not very good statistic, but we can see that there is some kind of a characteristic time scale of order of 5 picoseconds. And the drop is of order of 40%. So basically, when we excite the material with femtosecond laser pulse, magnetization of holmium drops very fast on the time scale of several picoseconds, while magnetization of iron doesn't really change at this time scale. So, and this study investigating this kind of dynamics, so this is a contrast at holmium and at iron plotted together, we suggest the following scenario for switching. So basically, first, what we have is ultra-fast demagnetization in holmium. So it means that before the excitation, we have holmium magnetic moments was larger. Therefore, the holmium magnetic moments were along the magnetic field, and iron was opposite the magnetic field. Then 40% demagnetization of holmium happens, and therefore, clearly, this is not any more stable situation because now the net magnetic moment is pointing in that way, and it's against the magnetic field. So what happens then to the magnetizations, how they start to move? Actually, if we look more carefully at this kind of dynamics, we see this kind of a cosine, half of a cosine like function. It means that iron and holmium, when they appear to be in such situation, they just start to coherently rotate in order to align with the field. And it's all the slow process of orders of several hundreds of the picoseconds, well, and it's complete over here. So basically here, by really doing pump probe spectroscopy in X-ray range, we were able to demonstrate that indeed there is a different response of magnetic moments of holmium and of iron to ultrafast excitation. I forgot to mention the excitation was 400 nanometers wavelengths. And we believe that it's still due to heating. And what is most important, we see that there is a fast drop of magnetization of holmium, and this triggers the whole dynamics, which allows to switch via the compensation point. And with this, I would like to thank you for your attention.
Thank you very much for nice talk. Colleagues, have your questions?
Alexandra, thank you very much for an interesting talk. I wanted to ask if you tried to calculate the heat or to calculate the heating, the laser heating.
Yes, sure. For the first part of the, basically for experiments with metals and for experiments with orthoferrites, it was done. And heating depends, of course, on the fluence. Mm-hmm. It's of order of, in metals, it's usually up to 100 to 200 Kelvin. Mm-hmm. In rare orthoferrites, of course, depending on absorption, but it will be several Kelvin or several tenths of Kelvin.
Mm-hmm. And what's the dependence of temperature reducing with time?
So how it relaxes?
Yes, yes.
This is much slower process. Typically, it takes microseconds or milliseconds. Well, this is kind of a disadvantage of this process because when we, for example, triggered this ultra-fast transition, spin orientation, afterwards, after this milliseconds, the material goes back, unfortunately. Mm. But for this switching via compensation point, if we, for example, somehow find a way to remove the field, then in principle, if we have switching, then it will stay there.
Mm. Okay, thank you very much.
Questions?
Спасибо за доклад, очень хороший. А вот скажите, пожалуйста, а на ком этой установке вот делался магнитоциркулярный дихроизм?
Да, это делалось на синхротроне Бесси в Берлине. Сейчас у нас есть некоторые проблемы с этим. Установка — это так называемый фемтослайсинг. Это когда обычно у синхротрона длительность импульсов 80 пикосекунд. Это очень много. Поэтому в каком-то месте в кольце его замешивают с коротким фемтосекундным лазерным импульсом. Это приводит к тому, что в кольце, в этих bending magnets, очень малая порция электронов отклоняется. Они немножко в другом направлении излучают рентгеновское излучение, рентгеновский свет, и поэтому мы получаем вот эти очень короткие импульсы.
А вот есть такие же эксперименты на XFL там сделать?
Сейчас это как раз развивается, да, там вот на том же XFL европейском, там они очень ждали, во всяком случае, пропозалы как раз в этом направлении. Да, конечно.
А вот деградации материала не происходит при вот исследовании? Там флаксы маленькие, да?
Ну, мы использовали те флюенсы, которые не повреждают. Конечно, можно повредить, но мы всегда за этим следим.
Okay, there is question online from Alexander Alexandrovsky. Is the mechanism of demagnetization purely phononic, or is there any dependence on quantum numbers of excited states? Purely phononic
Yes.
and dependence on quantum numbers.
If I correctly understand the question, well, what is important, what is the, well, basically very important process here, that phonons, phonons are responsible for increase of the temperature. And then this increased the temperature leads to the repopulation of the crystal field split levels in rare earth. So basically, in this sense, we can say that it's, I don't know, is it correct to call it change of the quantum numbers? Yes. Yeah, that's, we believe that it's like that. So phonons, they, well, basically, they absorb the energy, temperature is increased, and then rare earth reacts by repopulation of the levels. Well, I don't think I can answer this question. In principle, I'm not really sure what is meant by this question. Dependence on quantum numbers. Yeah. Oh, okay.
Have you questions?
Thank you very much for the nice talk. And I would like to ask you, clarify what is the mechanism of the effect of the circular polarization radiation on the reference spin reorientation to the one phase or another
one? Sure. Basically, first circular polarized light. Circular polarized light is known to be able to excite the precession. Yeah? The microscopic mechanism is so-called impulsive stimulated Raman scattering. Basically, it's a generation of magnons, of coherent magnons, when this femtosecond laser pulse scatters in the material. It's like Raman scattering. So we have excited precession. It means that magnetization starts to move to one way or another, depending on the polarization of light. Now, so we started from this situation, and now basically our magnetization have to choose whether it will reorient this up or down. So, and then depending on the helicity of light, the initial phase of precession will be also forcing magnetization to start to precess basically up or down. And since the typical characteristic period of the precession of magnetization in these materials is comparable to this time, so it's also of order of 10 of picoseconds or so, then we have this kind of then when these two minima emerge, magnetization is not in this original position, but a little bit deviated up or down, and basically that's why it goes here or here. That's our model. Or maybe we can discuss later
Thank you.
more details.
And last short question. Thank you very much.